So basically, for number 3, you're going to prove that at some point, it's going to cross through y equals -5. Okay, so you basically just use the function to prove that there has to be a point where h of r equals 5 or -5. So I have to erase this. So it wants us to use IVT to prove that between for the function h of, I guess it's r, h not h of x, h of r, between, so r is between, I think it was 1 and 3, and hang on. There exists a point where h of r equals -5. So, the first thing we need to prove is that it's continuous on this interval, which would be 1, 3. Not including 1 and 3, because it does not have the lines under the inequality signs. So how we would do that is, well, basically what it gives us is that f of x and g of x are continuous for all real numbers. And I forgot to add the -6 on here. Was it a -6? It was a -6. So h of x and g of x are continuous in all real numbers, meaning that we can say that because h of r is just f of g of x minus 6, we can say that because we can say that h of r is continuous on all real numbers because its pieces f of x, nope, that is not, f of x, g of x, and f of x and g of x are continuous on all real numbers, and therefore f of g of x minus 6 is continuous on all real numbers because by the definition, and I'm just going to say of polynomials because I'm not really sure what the -6 would make this, but I'm not really sure how else to classify this. So I'm going to say polynomials, and this is not a formal definition at all, so maybe I would lose points for this since it's an FRQ. However, h of r is continuous in all real numbers because it's all of its pieces, the f of x, the g of x, and the -6 are all continuous. That's basically what it's saying. So since all of its pieces are continuous, it's continuous in all real numbers. And because it's continuous in all real numbers, because it's continuous on all, I guess I should probably write the symbol for all real numbers. All real numbers, h of r is continuous on the interval, and there are symbols for this. I don't remember them, so this is not a formal definition and would lose points, but on the interval 1 to 3, not including 1 to 3. Now, we need to find out what h of 1 are and h of 3 are. because we're trying to prove, remember, basically n is -5, and we're trying to prove that it goes to -5. So, h of 1 is, well, first we would plug in 1 into g of x, which is 2, and then we would plug that 2 into f of x, and that would be h of 1. So f of 2 is 9, so h of 1 equals 9. And then we do h of 3. And that is a z. Now there's an equal sign. Alright, h of 3. So you plug in 3 into g of x, you get 4, so then you plug 4 into f of x, and you get -1. So h of 3 is -1. So now, oh, I forgot to do the -6. Okay, so it would be 9 minus 6 equals 3, my bad, and then -6 equals -7. So h of 1 equals 3, h of 3 equals -7. Okay, that makes a lot more sense. This is what that is. So now we just need to say that, like, we know that -5 is between -7 and 3, and because it's continuous on from 1 to 3, we know that h of x has to go through -5, based on that previous video. So, basically what you're doing is you're proving that there is a line where h of r equals -5 on the interval 1 to 3. So, or there's a part where the h of r equals -5. And because we know -5 is between h of 1 and h of 3, and we know that it's continuous from 1 to 3, then we can say that there exists a point on the interval of on that interval where h of r equals -5. There is a formal way to say this. I'm going to look it up real quick. Okay, so basically, you would say, by the IVT, there exists a value in, okay, that is not what that looks like. In the range, or in the, I don't remember. A value in the range of, in the interval 1, 3, such that h of r equals -5. Alright, that's how you do that. I hope that helped. If that did not, let me know, and I will try to help you. Okay, goodbye.